Okay, so is work being done in question number 1? I sure hope so. Okay, because what's changing in here? The speed. If speed is changing, are you changing kinetic energy? Okay, that's what we have to realize. As soon as you see that it's accelerating, okay, you have to do work in order to make something go faster, right? Okay, and that's kind of the train of thought that we have to have when we're reading a question that has to do with work energy theorem. Okay, what's happening here? Is it moving higher? That takes work. Okay, is it moving faster? That takes work too. Okay, things don't just accelerate for no reason. Agreed? Hopefully they don't anyway, otherwise everything I know about physics is out the window. All right, so that takes energy. Work, okay, is a change in energy, and in this case that means that force times distance equals EK final minus EK initial. It's just for the first time, EK initial isn't 0. All right, it's some other number this time. Does that really make a big difference? Not really. We've always been subtracting 0, we just never bothered to write it. Okay, now we're actually subtracting a number instead of 0. Okay, doesn't make the question really any different. All right, is everyone following where we're going from there? Okay, once we get whatever this side equals, can we find the force? Yeah, because we were told the distance was 13 meters. All right, so what that looks like from a mark's perspective here, give them 1 mark for their givens. Okay, so 200 kilograms, VI is 2 meters per second, VF is 8, D is 13 meters. Okay, give them a mark for recognizing it's a work energy theorem question. Okay, or if they wrote F times D equals 1/2 mvf squared minus 1/2 mvi squared, that would be fine too. All right. Now, in order to get force, we have to divide both sides by D. So I just bring D over here. All right, everyone okay with that? Okay, so give them a mark if they have that manipulation, okay, or they showed change in energy over D. They divided something that was in joules over D, okay, they're good. A mark for plugging in their numbers, okay, hopefully they did that somewhere. It doesn't have to be exactly like this, okay, but as long as they showed it. All right, so that would be 1/2 times 200 times 8 squared minus 1/2 times 200 times 2 squared over 13, okay. When we do that, we should get 461.5 newtons. If they rounded to 462 or whatever, it's fine, as long as they got 461. We'll say they meant change in EK and say that that would be okay for a mark. All right, any other questions on that one? Mac? No, I don't subtract, because I don't want the change in velocity. I want the change in energy, and that's different. Right? Because energy has to do with not just the speed, but also m. So you went 1/2 m and you went times 6 squared? Yeah, okay, but you can't do it that way because m is also a factor here. Follow me? It works for mgh, right? We could do that for m times g times h minus m times g times h. We could do it that way because h isn't squared. If you wanted to do that subtraction, you would have to go 8 squared minus 2 squared and then plug it in. Then you could go 1/2 minus whatever 8 squared minus 2 squared is. 60, I guess. Yeah? Does that make sense? Okay. All right. Any other questions on that one? Okay. All right. So in our second one here, obviously work is being done because they tell us, okay, that the crane does 450 joules worth of work. All right. That's the change in what kind of energy for this question? Potential, because we're lifting the load 13 meters. Okay. Or sorry, to an unknown height from 13 meters. So again, instead of our initial energy being 0, our initial energy is something other than 0. Does it really change what we do? Work is still a change in energy. We still subtract initial from final. Okay, so give them a mark for their givens. 65 kilograms. Okay, HI is 13 meters. Okay, work is 450 joules. Right, for W here, we got change in energy. Okay, or work equals mghf minus mghi, or maybe they just went work equals m times g times the change in h. Either one will be fine there, okay, for a mark. Then we have to manipulate in order to find, okay, the final height. So in order to do that, okay, and this is sort of the thing that some people mess up on the manipulation. If I want to get HF by itself, the first thing I need to do is add this term over to that side. Agreed? Can I do that? Okay, so W plus M times G times HI divided by MG. Okay, that gets the MGs to cancel there on this side, not on this side. Okay, and we're left with HF. All right, so if they manipulated, give them a mark. Give them a mark for plugging in their numbers, 450 plus 6.5 times 9.81 times 13, or maybe they just plugged in what that equaled, okay, over 65 times 9.81. Okay, gives them HF, and HF should come out to 13.7 meters. Okay, so you are aware. That's what I did, but I'll do it again. Okay. All right. Okay, so let's just have another look at it here, guys. Okay, everybody watching, okay, because if one person's having trouble with this, chances are a lot of people did not get 100% and you need to watch. Here's why you need to watch. These were on last year's unit exam, both of them. They were the Work Energy Theorem questions first semester, not second, because I've already given you the ones from second semester on the quiz before. Okay, so you know what I'm going to ask here, so it's important to watch. Okay, work is a change in energy. We changed what kind of energy in this question? Potential. So that's why I'm doing this step here. Work equals M times G times HF, the final potential, minus the initial potential. With me there? Okay. I need to get HF by itself. Okay, so in order to do that, I need to add M times G times HI over to this side because I'm subtracting it. Okay, with me there? All right, so that leaves me with this. Work plus the initial energy. All right, does that make sense? If this is the change in energy, if work is the change, and I add it to the initial, that should give me the final energy. Okay, everyone's okay with that? All right, so that's M times G times HF. I need HF by itself, so now I can divide both sides by M times G, and it comes over here. All right, that leaves HF by itself. Now I just plug in my numbers and solve. Okay, so that's 450 joules minus M, which was 200, right? Or sorry, 65. 65 times 9.81. Sorry, times 9.81 times the initial height, which was 13 meters. I cannot cancel the mg's, no, because this operation has to happen first. Okay, I have to have joules on the top divided by newtons on the bottom in order to get meters. Okay, all right, so I do that part. Okay, first. Okay, joules minus joules. Okay, divided by 65 times 9.81. Okay, and that should give me my, what did it come out to? What was it? 3.7? 13.7 meters. Okay, does that make a little more sense, MJ? Okay. All right, any other questions there, guys? Okay, does that deviate from the pattern that we have done in the past? It does? Is it work is a change in energy, final minus initial? Okay, that's what I mean though. That doesn't ever change. What may change is that you may have an initial energy as opposed to having an initial energy of 0. Okay, but in the end, we didn't do anything really different. Okay, it was still a change in energy. All right, is everyone okay with that now that they've seen it? Okay, do we want to spend a little bit more time on work energy theorem today? Okay, that's kind of what I thought. I was looking at maybe moving on to conservation of energy, but okay, we have time. We can spend another day on work energy theorem. All right, give them a mark out of 10. Let them see it. Put it in the box. Okay, so I've had one like this, I think on an old IB exam back when we had Science 10 IB. Okay, so it would be like an AP kind of question. All right, car applies its brakes, okay, with a force of 10,000 newtons, causing it to slow from 20 meters per second to 6 meters per second. If the car's mass is 1,700 kilograms, how far does it travel as it slows? Okay. Is work getting done? Yes. How do we know? Okay, because it's accelerating, and if it's accelerating, what's changing? And not just speed, energy. What kind of energy is changing? Kinetic, right? Because kinetic has to do with speed. That's just something we have to remember. Okay, kinetic energy has to do with changes in speed. Potential energy has to do with changes in height or shape. But we're not dealing with elastic, so okay. So in a question like this, it's important for us to recognize that first off. And before I even do givens on a work energy theorem question, I write down work's a change in energy, and if it's only one kind of energy, which it is for you guys, okay, I write down which kind. Okay, and I say work is a change in kinetic energy. Right? The trick is to recognize that because the speed of the car is changing, okay, kinetic energy is changing, and that means work is being done. Right? How on a test would you know that this is a work energy theorem question and not a question about acceleration? Okay, exactly. You got to look at what you're given. All right. This question mentions force, it mentions distance, okay, and mass. Would you get any of those things in an acceleration question? Right? In an acceleration question, you'd get VF and VI, which is why this can sometimes be confusing. But you would have got time or acceleration, okay, instead. Right? I didn't give you time in here. Do we ever deal with time and energy? No. Okay, time is never a factor when we're dealing with energy. So, okay, it's a matter of being able to identify. How can we identify it? Well, we can write down our givens. Okay, when we write down our givens, which formulas are involved becomes pretty clear. Right? We know the force, 10,000 newtons. Okay, it asks us about distance. We don't know what it is, but we'll figure it out. Okay, we know that VI is 20 meters per second, and we know that VF is 6 meters per second. All right. So we said work is a change in kinetic energy. All right. So let's write that out a little bit differently. Formula for work is, or one of the formulas for work, force times distance. Okay. Force times distance equals the change in kinetic energy, which means, okay, the final kinetic energy, 1/2 mvf squared minus 1/2 mvi squared, the initial kinetic energy. Okay. Now, because the energy is decreasing, is it possible that I might get a negative number here? It is. That's fine. Okay? It's only because the work being done is causing the car to, yeah, and as a result, it's losing energy. So it's doing, essentially, the car is doing work on the brakes. Okay? The brakes are going to get hotter. They're going to absorb, okay, and get thermal energy as a result of the kinetic. So from the car's point of view, this is negative. Right? From the brake's point of view, it's positive. If you get a negative number here, don't worry about it. All right? I'm asked to find distance. How far did the car travel? So what do I have to do to the formula? I have to divide both sides by f, right? Okay. All right, so that leaves me with D. So can I plug in my numbers now? Am I to that point? Yeah. All right, so D equals 1/2 times 1700 times 6 squared minus 1/2 times 1700 times 20 squared. Okay, over 10,000 newtons. Okay. Now, the top's going to be negative, agreed? Okay. That force that the brakes are exerting, forward or backward? Backward. They're causing the car to slow down. Is that a backwards acceleration? So if you don't like the negative number, you can just make the 10,000 negative. It is backwards after all. Okay? But again, it doesn't really matter. You're going to get a negative number for distance if you don't do it. Okay? Just understand that doesn't mean the car actually went backwards. Okay? All right. So when we plug in our numbers here, okay, we punch it into our calculator so that it looks like this. Okay, so in brackets, so we get the whole top here. 0.5 times 1700 times 6 squared, okay, minus 0.5 times 1700 times 20 squared. All right, so there's the whole top, okay, divided by the bottom, 10,000. Okay, so the car traveled 30.9 meters, okay, in doing all of this work. Okay, on a test, I would probably not give you one that ended up being negative, right? Just because it would probably throw people a little bit, right? But still, the method of this question is like what you might end up with on a test. Is this very much like the first question we did on the quiz this morning? Yeah, okay, pretty much the same thing actually. Right? Does that one make sense to people? Okay, so again, the initial energy wasn't 0 this time. Didn't change anything. Work was still a change in energy. Okay, we still subtracted initial from final. Okay, anyone need that one anymore? Okay, so in this one here, we got a slingshot that's aimed straight upwards in the air. Okay, it's drawn back 0.4 meters with a force of 1,500 newtons, and the rock reaches a height of 30 meters. All right, we want to find out, okay, what the mass of the rock is. We're going to assume that this slingshot was fired from ground level. All right, if they don't say otherwise, that's what you assume. So what's the initial height? 0. What's the initial potential energy? 0. All right. So that said then, what kind of energy is being changed in this one if we're dealing with height? Potential energy. All right, so we know that our initial height is 0 meters. Okay, our final height is 30 meters. We don't know the mass of the rock. Okay, we know the force, 1,500 newtons. I think this rock is going to be ridiculously large, but that's what happens when I pick numbers out of my head. And the distance here is 0.4 meters. Okay. Is work being done? How do we know? There's a change in energy and a force was exerted over a distance. Okay, both qualifications fit here. Work's a change in potential energy. All right, so force times distance equals m times g times hf minus m times g times hi. Everyone okay with that? Okay, sorry. Now, with this one here, okay, I'm being asked to find mass. That's a little bit tricky because mass is in two places, isn't it? But what's this term? 0. Okay, the initial energy was 0 because the initial height was 0. Now is it tricky? Not at all. Okay, now we're just looking for m. So we divide both sides by GHF. All right, so we got force times distance over GHF equals m. So 1,500 times 0.4 over 9.81 times 30. This is going to be a really heavy rock for that slingshot. Okay, so 1,500 times 0.4, 600, okay, divided by a 5-pound rock. But, okay, it's all right, whatever. It's a 2-kilogram rock. Okay. It's a big slingshot. Nobody said how big the slingshot was. I mean, it was drawn back about that far. That's a pretty big slingshot. So, okay, so it's a 2-kilogram rock. Any problems with that one? Yes? No? Okay. All right, so in this example, you're on a ladder, and I think from the numbers I chose, it's going to be a very long ladder. Okay, 4,000 joules of work is done on a 25-kilogram box carrying it up a ladder from 7 meters. So we started on the ladder 7 meters above the ground. Okay, we are looking for the final height of the box here. Is Is work being done? How do you know? Okay, not only is there a change of potential energy, but the question says 4,000 joules of work was done. Always a good indication of a work energy theorem question. Okay, sometimes I'm actually that blatantly obvious. All right, it said work was being done, so we know that energy is changing, and we know in this case that it's potential energy because height is mentioned a whole bunch of times in the question. All right, again, those are the things we have to look for when we're determining what type of question is being done. All right, so we're looking at mass, 25 kilograms. Okay, we're looking at energy. Okay, change in energy. Work, 4,000 joules. Okay, initial height, 7 meters. Final height, unknown. Okay, so work is a change in energy. And they told me what the work was. I don't even have to do force times distance on this question, do I? Okay, so that part makes it a little bit easier, actually. So we got change in energy, so work is going to be m times g times hf minus m times g times hi. I want hf by itself. What do I have to move first? mghi. How do I do that? Add it to both sides. Right, remember, work is a change in energy. If I add the change to the initial energy, that should give me the final energy, and that's what I'm looking for here. All right, so work plus m times g times hi gives me m times g times hf. How do I get hf by itself? Divide by mg. Okay, remember, mg does not cancel here. All right, that is the most common mistake made in here, all right, on a question like this would be to cancel mg. mg does not cancel because this part would have to be done first. Okay? So, we've got 4,000 joules, okay, plus 25 times 9.81 times 7 over 25 times 9.81. Okay, that'll give us HF. Is it like a couple hundred meters? It's a very long ladder. 23? Okay, well, let's punch it in here. So 4,000. Oh, it works better when it's on. Yeah, so 23 meters. So this would be like one of those ladder trucks. Okay, like those funny fire trucks with the big long ladder on them. All right, so 23.3 meters. Okay, is our final height. Questions on that one? Okay, is this making a little more sense now? Okay. Hey, we'll do one more here on kinetic. Okay, so this would be a very verbose question. Verbose means it uses a lot of words when it probably didn't need to. Okay, but sometimes questions will do that, especially when you get to grade 12 in any of the sciences on your diploma exam. They just love to tell stories, okay, on their questions, and it takes you forever to read the questions and actually get to the point where you're doing something, okay? And in the process, sometimes people get lost, confused, they forget what they were given or whether they actually needed half the stuff they were told, okay? So, in this one here, what kind of energy is changing? Kinetic. Take a question. It does. That was one of the things I did to try and trick you, okay? So, kinetic energy is changing, and I gave you the mass in grams. You can't use grams, because grams won't give you joules. You got to convert it to kilograms. Is that very hard? Okay, 650 grams is how many kilograms? 0.650 kilograms. All right. We're trying to find the force used to compress the spring on this toy car. So, distance is 0.23 meters. Mass, 0.650 kilograms. Okay, initial speed, 1.2 meters per second. Final speed, 3.1 meters per second. In this question, the kinetic energy is what's being changed. All right, so force times distance okay, equals 1/2 mvf squared minus 1/2 mvi squared. If I want to find force, what do I have to do? Divide by distance. Okay, can I plug in my numbers now? Yes, okay, I'm to that point. So force is going to equal 1/2 times 0.650 times 3.1 squared minus 1/2 times 0.650 times 1.2 squared over 0.23. Okay, so we got 11.5 newtons of force. Okay. Okay, expect any one of those examples to be an exam level question. Okay, on work energy theorem. In fact, most of the time, they're not quite that involved. Oftentimes on a test, the initial energy is 0, or the final energy is 0. Okay. All right. Get back to work on that worksheet. Okay. Obviously, we haven't gotten far enough into that worksheet yet. Okay, so that's what I want you working on for the last 10 minutes of class here. Okay, if you have questions, just ask and we'll go over them.